We're going to have Andy Eschbacher come on, who is from our tech team. He's from the research team working in spatial data science, and he's going to teach us a black belt in spatial data analytics. Fun fact about Andy is that he used to be a high school physics teacher, but now he's here at CARTO, changing the world of location intelligence. So please welcome Andy to the stage.
Thanks.
Clicker.
Cheers. Hello. Oh, great. OK, let me see if I got the directions. OK, great. Hello again. My name is Andy Eschbacher. I'm on the research and data team here at CARTO, or the data science team. I'm giving this talk in place of my colleague Stuart, who couldn't make it because of just some visa problems, essentially. So if I'm going to give it in its place, so I hope I can summon my inner Stuart and give as good of a talk as him. OK, so the talk that I wanted to give today, we wanted to highlight some of the projects that we've been doing on the data science team and at CARTO in general, and how it interfaces with traditional GIS, and what we generally do is spatial analytics here on our team. I wanted to highlight some projects that we've been doing, kind of the landscape of spatial analytics, where we're going, and how CARTO fits into various solutions along the way. So I wanted to start out by just defining what traditional GIS is, or how we see it here. And go the other direction. Traditional GIS focuses on three main areas. So the organization of your data, so geographical information systems. You need the data stored in a format that's comprehensible. The visualization and the calculation part. We see those as the three main parts of traditional GIS. For the organization, so in CARTO, you have your dataset dashboard, which is a view of a database or a table in a PostgreSQL database with PostGIS installed, which is how the geometries are represented here in CARTO. There are other representations of that data, obviously, but this just represents the organization of a traditional GIS. The visualization aspect of GIS is very important for communicating the results visually. And then finally, the common GIS operations. This is how most people, I think, see GIS, as a series of basic operations that you're performing on your data sets to gain some understanding of those. A lot of these operations that you have, they're kind of like basic mathematical operations, but for the GIS space. And so you can think of them as analogous to like primitive operations that you would have in mathematics. Some of them are binary. They work on two different variables at the same time. Some of them are unary. But really, they form kind of like a basic mathematics of some sort for the GIS landscape. GIS is focused on visual exploration and answering questions. Like you can say how far. So in PostGIS, we have ST_distance. So it's a binary operation. You have two geometries, and you want to find the distance between those. How many are in this area? So that would be something like a count, or maybe a point and polygon sort of operation. How big it is, so that could be area, or the bounding box, or any other operation that's similar to that. Where are these things? So maybe you would have some more context of where did this event occur based on some geographic boundary. And what's the closest to? So you might have like some nearest operation that you're trying to understand. Spatial analytics, on the other hand, is more focused on questions that are maybe higher level than some of these basic ones that you'd see in traditional GIS. So what is the likely cause of a pattern that you're seeing in your data? To answer a question like that, you might pull from traditional GIS and put some of those operations together. But you're looking for a deeper understanding than the operations that would be in traditional GIS. Other questions, how much of an effect does this one thing have on another one? A lot of these are very, very much similar to data science questions, but they have a spatial component to them. Where are the places where something unusual is happening? So maybe there's some type of hotspot analysis that you need. How can I organize things to better reduce costs? So maybe an optimization problem. What would happen if I tried to do something similar over here? So based off of previous patterns that you understand in other places, how can you apply that to a different context, perhaps? And another question could be, what will happen in these locations tomorrow? So more of a predictive behavior. One way that you can start to organize the sorts of questions and analyses that you would have in spatial analytics, the very kind of the cornerstone for understanding any data set is to just do some descriptive analysis. So this might just be some basic statistical questions you can ask of your data, like what is the average, what is the median, what is the variance in my data set. More diagnostic questions where you're trying to understand what has happened. And as you can see on the way they're kind of plotted on these two axes here, the further to the right, the more difficult they tend to be, and then the further up on the y-axis, the more value somebody might get from these. So this descriptive is just describing like what happened. It's maybe more of a data summary. You're just describing the data that you have there. Diagnostic would be what caused it to happen. So if you see a sudden drop in prices in a certain area, was there some event that triggered that? Predictive, as we all know, tends to be very difficult, especially to do well. So you're asking what will happen based off of things that have happened before, perhaps. And then prescriptive is trying to more engineer changing future events instead of predicting future events. So how can I make X happen? So this is like a doctor giving you a medication to try to take care of a problem that you're having. You can see as a spatial analyst looking at the data that is there. Maybe you do some sort of optimization problem to try to arrange your operations differently so that you will reduce the cost or something like that. One way to demarcate these different types of analyses between traditional GIS and spatial analytics is this vertical axis that we drew here. Traditional GIS is very good at the descriptive part. It really gives you a sense of like a ground truth of some way to try to understand your data better. It can go into the diagnostic a bit more, but it doesn't really go much further than that. Spatial analytics uses some of these traditional GIS techniques to put together these more complicated solutions to the questions that you have and give you answers. A good analogy that we found for looking at this, there's an astronomer and scientist who has done a lot of really interesting things in his life, who has this nice quote: "Data is not information. Information is not knowledge. Knowledge is not understanding, and understanding is not wisdom." We felt that this was very analogous to those four different types of answers or questions that you have of your data. And to expand on this more is data isn't information. Information, unlike data, is useful. While there's a gulf between data and information, there's a wide ocean between information and knowledge. What turns the gears in our brain is not information, but ideas, inventions, and inspiration. Knowledge, not information, implies understanding, and beyond knowledge lies what we should be seeking, which is wisdom. So this is what we all aspire to, I think, when we're solving our problems. But I think it's a good thing to aspire to. So we saw the different types of problems that you might have. And then on our team, we see these as three different domains of tools that you can use to solve these problems. So the first one is inference. One analysis that people commonly use in spatial analytics is outlier and cluster analysis. So there's a whole collection of different analyses. The one we're doing here is Moran's eye, so it's spatial autocorrelation. And the backstory behind this is there was an earthquake, which you can probably identify where the earthquake occurred. And I come from a family who is very much interested in geology for just random reasons, and my dad sends me emails every time there's an earthquake in a weird place. He gets tons of emails from the US Geological Survey. And I don't know if he's ever felt an earthquake, but he's always wanted to. He's interested in natural phenomenon like that. And so there was an earthquake in Oklahoma, which is kind of in the center of the map where you see a lot of the orange there. And my sister felt it, and she lives in Kansas City, Missouri, which is just a little bit northeast of here. But my dad was sleeping at the time, and he didn't feel it. And when my sister emailed our family to say that she felt an earthquake, which was pretty exciting, it was a pretty minor earthquake. She just felt the ground rumble a little bit. My dad was pretty bummed. But I was working on outlier and cluster analysis at CARTO at the time to bring it into our platform. And I started to wonder, could we use social media data to try to uncover patterns in like natural phenomenon like earthquakes and things like that. And so in that case, humans would be the sensors to detect, and then they would just be communicating that data to the web, which we could then collect and then try to uncover patterns in it. And so what we did here is we got as many tweets as we could around the time of this earthquake event. We aggregated them to the county level here. We ran the Moran's eye off of it. And the styling, if you've used Moran's eye before, it gives you an idea of whether your geography has high values compared to your neighbors and high values compared to the global. And so you can have a cluster of high values, you can have clusters of low values, or you can have outlier values, which are areas of high and low, or the opposite of that. And you can see that there's this big cluster in Oklahoma where people were tweeting about feeling an earthquake. And if you know anything about fracking, which is extracting natural gas, there's been a lot of earthquakes in there because of this activity of extracting natural gas there. But the cool thing is you can look through the data at Twitter, identify certain keywords, just run it through an analysis like this, and you can make an inference that you can make an inference that there was an earthquake happening. And for these inferential techniques, they're just your first step to try to understand the data and try to look for a pattern in the data that you don't necessarily know is there. And then once you can make an inference off of it, you can do more advanced analyses. Another case study that we did on our team for uncovering patterns in data sets, this one uses dbScan, which is density-based scanning. So it's looking for clusters of areas where there are similar densities of points that are there. And my colleague Wenfei did this analysis of GPS data to look for patterns in how people use Central Park. And she identified many places and was able to look back at the map and then identify some of those places on a map as where Strawberry Fields, where there's a John Lennon memorial, for instance, things like that. And then from this, you can also infer modes of transportation and generally how people use the park. So a lot of this is still inference-based. So you have this data, you see some new patterns in it based off of this analysis you're doing, and once you have those new questions, you can go further to try to understand it better. Another case study is looking for, there's a NYC Pride Parade. You can look at taxi data to see where people are picked up or dropped off to try to understand what people's behaviors will be before or after events. So another technique, another suite of tools that we have in our tool set to try to answer questions with spatial data is optimization. And this is kind of a long video here, but what I'm doing in this video is I created a custom analysis in CARTO. It's something I'll talk a little bit about later, but in CARTO you can create these analysis nodes. You can chain them together. It's a directed acyclic graph like I was talking about in my CARTO frames talk, but for Builder. You can create these custom nodes, and right now we're working on building out a lot of these different custom nodes to look for use cases for CARTO Builder and other applications. So if you're interested in making a custom node in Builder, follow up with me later and we can talk about some use cases. But this is a very specific example that required a significant amount of development. The goal here is that these orange areas are areas where waste needs to be picked up for processing, so it could be recycling, it could be just municipal trash, or it could be industrial waste that needs to be processed in a certain way. And then the blue areas there are the plants that would be doing the processing. The numbers above the sites are how many tons are there, so roughly like 2,000 kilograms. And then the connection between a site where the waste is produced and then where the waste is processed is the output of the algorithm deciding that that was the most optimal one to connect it to. There are a lot of different scenarios that you can have. In the scenario here, there's a lot of excess capacities in the plants, and so you end up with something very similar to a Voronoi, so you go to your nearest processing plant. But you can imagine if you have a very constrained system, the plant doesn't have that capacity, so you need to send it to maybe the next farthest or the one like beyond that. But when you do the optimization, it looks at the world of possibilities for all of the combinations of all of the sites and all of the plants and decides what is the least costly one. The way that geospatial came into this, right now I'm visualizing it with straight line distances, but the data that I'm using for deciding how far it goes is the road network. And so I use Valhalla, which is an open source routing engine, and I loaded up the road network from OSM, from OpenStreetMap. You can do something very similar in CARTO. And so it's using the road network to decide which one to send it to. So you, generally for the cost model, the further you send it, the more expensive. It's pretty linear there. Some other decisions is some of the larger processing plants are probably cheaper to do the processing, and some of the smaller ones are more expensive. And then some of the processing plants always also process a special kind of waste, and so there's going to be a premium to process it at that plant as well. And so the full cost model is a combination of geospatial data, so how far you're going to send it from each site to any of the other sites, and then the gate fee, so if you can get it, the price to get it into that specific processing plant. You can see one of the outliers here. Most of these are just radial. They're just going to roughly the nearest. One of the outliers here is you can see site 10 is going to site 27. You can see that it's roughly orthogonal to it. And that one was a fixed one. You can see we have a widget on whether it's fixed or not. So a lot of them are free to go to whatever site you want, but some of them, maybe you have a special type of waste that needs to be processed. It's sent to a specific plant. And CARTO Builder is actually a really good way to explore this type of data set. And then beyond that, if you edit the underlying data set of waste sites and add a new point to it, Builder will re-trigger that analysis, rerun it, and you're going to see the whole network reassigned optimally so that everything is as cheap as possible for this one. Obviously, it's a model, so there's probably complexity beyond that, but the model that we decided on took into account enough reality that we felt comfortable going forward with it. So optimization. So a lot of these tools might fall into different categories. So I think that this one accounts for that kind of highest level one, which is prescriptive, because you're deciding how do I change things to give me a cheaper overall cost for the network. So some of the local decisions might be more expensive, but if you look at the global picture, it'll be cheaper in total. Other examples, you're going to see at Geographica's booth, they have an routing optimization one too, also on waste collection that's pretty great. So I recommend that you go to their booth and ask some questions about it. Prediction. So prediction is very exciting for a lot of people. It's also very hard. So generally, the questions you're asking for prediction is, given some existing data, can I predict some target value in a new area and at a future time? And so a lot of the times when you're trying to answer questions like this, you're looking at historical data. And usually the hard part for this is figuring out what data you put in at the beginning to try to give you better answers at the end. So how would we solve this problem? If you've seen the XKCD comic on machine learning, I think this is the best description of what machine learning is, if you've ever seen this before. So the first person asks, what is your machine learning system? Or this is your machine learning system, and the other guy says, yep. You pour the data into this big pile of linear algebra, then collect the answers on the other side. And then the other person says, what if the answers are wrong? The guy says, just stir the pile until it starts looking right. So if you've ever trained a machine learning model, this probably feels pretty familiar. You're always tuning hyperparameters, trying to get everything to seem sensible in the end. A lot of the time it seems more art than science when you're doing something like this. But I think this is one of the best descriptions of machine learning. But I don't use an OR when I'm training my machine learning models. Okay, so when you're doing prediction, oftentimes you need to create new features. Data is very, very messy, and so creating features, engineering them so that they make sense for inputs for your data is a lot of the times a lot of the front-end work, and then putting them into your model usually is easier depending on the type of model that you're doing. So the first thing you need to do is identify features that might have an impact on the variable of interest. So if you've ever done anything like this before, it's very much an iterative process. You're trying to discover things as you go along. Usually you don't know a priori what's going to be important and what's not going to be important, but depending on the model that you're doing, it'll help guide you on the importance of different features. The collection of features that you put into your model is usually referred to as X or capital X. Notations are different in different applications. They could be things like square footage, if you're talking about apartment prices or something like that. Or if you're looking at retail places, if it has free coffee or free beer, or, if you're thinking of maybe co-working space. Other things that have spatial context, you can use some of those base GIS functions that we mentioned earlier. How many businesses are nearby? How close is this to the nearest subway? Is there easy access for lunch? So that's very much, the example here is like a site selection sort of example. Picking features can be very hard depending on what you're looking at. A very traditional way of picking features is using the census of the country that you're interested in. Depending on the country you're into, you can have hundreds and hundreds of different measures that may or may not be important. Finding them at the geographic scale of interest to you could also be another challenge. But there's a very wide collection of census information that you can use. Like I said, this is the traditional way to begin building features for your model. One of the shortfalls of going this route, or relying totally on this route, is that it tends to focus only on people's home locations and people's work locations. And so if you're interested in people's nightlife or what people are doing on the weekends or anything like that, the census won't help you. It won't help you along the way. So as you saw in Javi's talk this morning, there are a lot of other data sources that you can rely on for things like that. So if you're using location data streams, you can start answering questions about what the foot traffic is in an area if you're looking to locate a new store or something like that. And so we're in an era where this type of data is becoming more and more commonplace. Trying to manipulate this data and use it for your model is a whole nother story, because sometimes you get terabytes and terabytes of this, but you're only interested in aggregations at a census tract level or something like that. So once you've decided on the features for your model and you've gotten all of your data to work out, you need your model to learn from your features. When you're building a model, a predictive model, or a descriptive model, you know your inputs, which are the features you've chosen, and usually you have a data set for training your data. So if you're looking at store, training based off of store sales. So there's a classic example from Foursquare where they used foot traffic data to predict iPhone sales. And So the input would be foot traffic data, and they probably had other features as well. And the output would be how many iPhones were sold. And then the hard part is figuring out what your function is. So is it going to be a linear function? Is it going to be something that you don't even understand because it's a really complex neural network that's really obscure? And then we use the data that we have and then the techniques of the model that you're interested in to try to approximate that model. And let me see if this will begin. Maybe I press it again. So what we did, see if the video will start. Oh, thank you. So what we wanted to do is try to recreate that problem solving. Oh, can you get the sound, please?
We're going to do that by looking at existing fast food restaurants, how much money they're making.
Can you turn off the sound, please?
That are the context of where they are. And we're going to build a machine learning.
Thank you. Okay, cool. So my colleague Stuart and I built this together. What's going on here is we wanted to try to recreate that problem. So what we're going to do here is pull up a data set of stores, and we have the amount of money people have spent at those stores, and we're going to visualize that here. And the y variable in our model is going to be the store sales. And so we want to try to predict the store sales based off of other features that we have in this data set. While that's kind of populating, you've heard a bit about Airship today. So Airship is this component or like a software development kit that you have for building dashboards. We built this with Airship. We did some custom analysis stuff too. So if you're familiar with a Postgres extension for spatial analysis that we created called Crankshaft, I built a custom version of Crankshaft that stores the output of a model so you can reference the model later if you have new data so that you can make predictions. And so what we're doing here, we're visualizing the data using a vector library. The larger the circles, the higher the store volumes. And so you can already start asking questions of this data. Are the store volume or the amount of sold in the stores related to the population density? Is it related to the size of the store? Is it related to a promotion going on? And what Stuart pulled up here on the right-hand side is we're adding those as features to our model. But before we even run the model, we want to examine those features on the y-axis versus our target variable, which is on the x-axis. Wait, am I getting that right? Wrong? I'm sorry. So what we wanted to do here is create a custom dashboard that's very much like CARTO. It pulls together disparate pieces of CARTO to build the application that we want to do from this. And this is something you're going to see a lot from us this year. We're trying to componentize CARTO so you can put it together again for the applications that you're interested in. This one is very much based off of prediction. We're also going to do one similar to the optimization one that I showed earlier. Some of them are just to highlight different analyses that we have here. But our goal for these dashboards is that you're able to put together the application you want more easily and more quickly. So some of the things that we're augmenting our model with here are the nearby businesses, so using some of the traditional GIS stuff. And on the right-hand side, you can see the lower, on the lower right-hand side, you can see feature importance. And so that's telling us how important that feature was in making the prediction there. So what we wanted to create with this is something that has this iterative aspect to it so that when you're training your model, you don't necessarily have to do it in code. You build the dashboard you want so that you can explore the data visually with the map, visually with the scatter plots or bar charts or whatever you're interested in doing. And you can think about building your model without having to necessarily code. So some people would prefer to do this in Python, and using CARTO frames, you can do something like that. But we also want to kind of hit the kind of middle ground between somebody who wants to be able to do this and explore and not really worry about the coding aspect of doing it. If you're interested in some of the other pieces going on here, the charts that we have there are from a React library called React Viz that was really easy to use. I recommend you checking it out. Same with the feature, this one's showing correlations between different variables as well. Yeah, I don't know, go on and on. Okay, cool. So building those dashboards, it's now possible with all the tools that you have with CARTO, including Airship and some other custom work. If you're interested in any specific use cases for custom analyses and things like that, please talk to us afterwards. We're very much interested in getting that feedback right now. What you can use today for those three domains of tool sets for solving the problems, for optimization, linear programming, and the client-specific logistics stuff that I talked about before. I'm happy to share that with you. For inference-based stuff, there's spatial clustering, parameter clustering, geographically weighted regression, Moran's-I and Geddes-Orts-G, and we have a collection of other ones. And for prediction, gradient boosting regressor, which is what was in that previous demo, geographically weighted regression. Once your model is trained and you have new data, you can use that to predict the new values, and spatial Markov chains. As all of these things mature, Engine is going to be more and more powerful. We see Engine suiting data scientists through solutions like CARTO frames, so programmatic access to CARTO. For location intelligence solutions, something like an analysis API, which you've probably heard several times today and we'll hear tomorrow, especially with Raul Ochoa's talk. Developers might use an analysis API as well, and then decision makers will use Builder or maybe custom applications like you saw that we built before. Prototyping in CARTO frames. So I gave a talk earlier on CARTO frames. It's our solution for data scientists who want to use CARTO but completely in a Jupyter Notebook setting or just in a Python script setting. And Builder through analysis nodes. So with CARTO frames, you're bringing CARTO to your analysis, and then through the analysis nodes, like the optimization one I showed earlier in Builder, you're bringing analysis to CARTO. So we want to make sure that we're fitting your needs into how you need to use CARTO and trying to make it as dynamic as possible for solving your problems. For location intelligence solutions, I mentioned earlier Geographica's demo, which is really great. The way they put it together I find really fascinating, but I think that they could speak to it better if you talk to them at their booth. And that's it. Thank you.